Just like a gravitational field describes the force that a mass feels in the presence of another mass, an electric field describes the force that a charge feels in the presence of another charge. So if we had some charge Q here and we placed a positive charge somewhere in the space around it, just say this central one was positive, what would happen? It would be forced away because it's like charges repel. If that charge was here instead, it would feel a really big force away because it's much closer, so the force is greater. If it were way over here, the positive charge would be forced away in that direction, but that would be smaller. So these arrows are an indication of the direction and size of the electric field. So in fewer words, electric field is the force per unit charge acting on the charge small q in the presence of another charge q, and we can write that in an equation form. So it's the force per unit charge, force divided by charge, and that gives you electric field strength. And of course you could work out the units of that. We know that the units of force are newtons, and the units of charge are coulombs. So the units of electric field are newtons per coulomb. And of course this force here is determined by how big the large Q is that's setting up the field. So the larger the Q, the bigger the force. An example here, find the electric field strength 1 centimetre away from an electron. Well, in the previous example that we looked at, we worked out the force between two electrons at a distance of 1 centimetre. And the charge on an electron that's caused this force is, of course, the 1.6 by 10 to the minus 19. And then we can simply just write the electric field is the force divided by the charge, which equals 1.4 by 10 to the minus 5. Don't forget the units, newtons per coulomb. Of course, we can think of this, just to review, that this is an electron. We can think of it as setting up a field, an electric field in the space around it. And if we plonk another electron in that space next to it, we've worked out what that force would be pushing that one away, which of course would be the same as pushing that one away, but let's just concentrate on this one. We've worked out the force. Now let's work out the force per unit charge, and that gives us the electric field at that point. And in the next slide we're going to look at a more generalized form of the size of the electric field, where we actually basically calculate what this F is and put it into the equation. So in this question we have a large charge Q, or just a charge Q, and it's located at a distance r from our test charge, if you like, Q there. So there's a distance r between them. And we're asked to find the electric field strength due to this charge Q experienced at that point, little q. So we're basically going to take our definition of electric field here, force per unit charge Q, because this is the one doing or experiencing the field of the other one, and we can also write down that the force between those two charges is KQQ on r squared, the distance between them. And essentially what we need to do is substitute this into that equation over there, and so we get E equals KQQ on r squared, all divided by Q. These Q's cancel, and we're left with E equaling KQ on r squared. And I've just rewritten that down the bottom, and this is actually the electric field strength at a distance r from the centre of a charge Q. Note that the electric field, let's use this one, the electric field depends on Q, because Q, this large Q, is setting up the field around it. It also depends, let me say what it doesn't depend on. It does not depend on what this value of small q is. It doesn't matter what charge you put out here that's experiencing the field. All that matters is the charge that's setting up the field and the distance from that charge. So this electric field only depends on the charge that's setting up the field, not what you're placing in the field. So in the next video we're going to talk about sketching electric fields.